All right, ladies and gentlemen, I hope you found the Chapter 10 test to be invigorating and easy. So today I'm going to show you how to do the problems from our first lesson of Chapter 11. So here we are. First problem. We have a one sample T statistic. This was my test. So in other words, it's one-sided. That's the key thing to notice. Based on a sample size of 10, this is the test statistic that's calculated. Okay, so question A, what are the degrees of freedom? Well, remember, degrees of freedom for the t-test would be n minus 1. So degrees of freedom are equal to n minus 1 for the t-test. In this case, that would be 10 minus 1, or 9. So 9 degrees of freedom on that test. Letter B, between what two probabilities on table C, because that's our T statistic table, will the p-value fall? Okay, so we grab our table, and we have to get a degree of freedom of 9, so that'll be on the first page of our table. Okay, so we go to degree of freedom of 9. Now, our test statistic was given as negative 2.25. Okay, here's the thing. Our table A was left-tailed, so that would have been fine. I'd just look that up and I'd find the less than. Okay, this table is right-tailed. Okay, so there are no negative values for our test statistic anywhere in this table. So to use it, look up positive 2.25. So we're just going to be using symmetry, okay? So anytime you're doing less than a negative, just flip it around and think greater than a positive. Okay, so I'm going to go degree of freedom of 9. That's this row. I'm going to read over until I get to 2.25. And you can see 2.25 would be just before, just a little below that. So that gives me a p-value between 0.05 and 0.025. Obviously much closer to the 0.025 because I'm just a little bit from that cutoff. So there we go. So our p-value between 0.025 and 0.05. Now, is that perfectly, right on the money? Well, no, it's a window, but it's a window that tells me I have moderate evidence, right? And that's good enough. That's what we need to do. We need to be able to say, oh, I have no evidence, I have mild evidence, I have moderate evidence, I have strong evidence, I have very strong evidence, right? So we don't have to have an exact p-value. This is good enough. But if you wanted an exact p-value, right, pull out your calculator and use it. Okay, moving on. Question 25. You're testing a null hypothesis that the mean is 0 versus a two-sided alternative. Sample size of 20. And the data is normal. Okay, what values of the T statistic are statistically significant at an alpha 0.005 level? Okay. So my degree of freedom here would be 19, right? So I'm going to be reading that row of my table. Now I have to understand that this is a two-tailed alternative, Okay, so when my alpha is okay, I don't want to look this up on the top, because if I look this up on the top, right, that's putting the entire alpha on one side. Okay, so I need to look this up, divide it by 2, because I need to split that in half. So 0.0025 is what I want to have on one side. So again, this, for some reason, this causes students a lot of difficulty, but if you need to, go ahead and draw a diagram, right? Since this alternative was not equal to, right? I got to take that alpha and I got to split it in half and share it between the two tails. Okay? So a one tail would be that, right there. So that's the column that I want to use. And my degree of freedom was 19. So using that column, reading down, this is the 19 right here, see? 3.174. That's my T star. Okay, is that all they wanted? Just what's the T star? Oh, what values of the statistic? Okay, so since it's two-sided, there's also a negative over here. Okay, so we'll be rejecting anytime we're in the tails, right? Is that what they asked? Rejecting? Yeah, statistically significant. So in other words, rejecting. So when T is less than negative 3.174, or when T is greater than positive 3.174, that's when I'd be rejecting or finding significance. Okay. All right. Next question. Oh, you have an SRS of 15, normal distribution. What critical value would you use to obtain a 98% confidence interval? Okay. So degree of freedom would be 14. And my confidence, 98%. Kind of a strange confidence, but they do that sometimes just to see if you can properly read the table, right? All right, so two ways to do it. You'll notice at the bottom of this page, oh no, the first page doesn't show confidence. So you can go at the bottom and figure out which column you need, right? Here's 98%, so you could count over and figure out what column that is. You could also, of course, look up to the top and say, oh, that's a 1%. Okay. Or, again, make a drawing. So if this is 0.98, right, then sure enough, that corresponds to a single tail of 1% on the right. So that's why that's the column. So I'm going to read that down to degree of freedom of 14. And there we go, 2.624. Oh, side note, some books, what they'll do is put a subscript on this so that the reader knows this is a T critical value and it came from this row of the table, a degree of freedom of 14. So that's a nice thing to do. I won't mark you wrong if you don't do that, but it's a helpful thing you could do on your T stars, right? I didn't do it on the last problem, so. Again, I'll accept it either way. Okay, moving on. All right, so the beginning of the assignment was just practice reading the table. Now we're actually going to put in to work the table as well as the actual calculation. So here we go. Vitamin C content. Researchers studying vitamin C were able to blah, 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 blah. Okay, so they have a product and they're afraid that, hey, over time, the potency is gonna deteriorate. So they have a reading when they have it in the factory, okay? And this is a sample. right? Each of these are just, this is part of a sample of a larger shipment. They get it to Haiti 5 months later, and they retest. Okay. So letter A, examine the question of interest, provide appropriate statistical evidence to justify your conclusion. So in other words, perform a significance test. Okay, so that's what we're going to be doing here. Okay. So when I'm doing this, the first thing I should notice is this is a matched pairs test, right? This is the same, okay? This is like one bag one bag that was measured at the factory, and then 5 months later, that same bag was measured when it arrived in Haiti. So it's a matched pairs test. This is dependent. I'm not interested in just this column. I'm not interested in just this column. I'm interested in the change, right? How much vitamin C was lost or gained. But, you know, the idea is, if anything, it should go down. So what I should be looking at is I had 44, then I'm at 40. So that is a loss of 4, right? So I'm going to change this data, and this first entry would be -4, right? My second entry would be -13, right? And so on and so forth. Matched pairs, I'm looking at the difference. So that's my actual data set, okay? So I'm going to let mu be the change, right? So it's going to be the Haiti reading minus the factory. Okay. So now my null hypothesis, nothing, didn't change, stayed the same, hence the word null. Now, alternative, you're not expecting it to gain, right? So I would go with a one-sided alternative because, right, over time, these things should lose potency. So I'm going to say less than 0. Yeah, here we are. A major concern would be some would be destroyed, right? Deteriorate. All right, so now we're going to run our test. So our checks. Does it say anything about normality? No, it doesn't say anything about normality. So I need to go ahead and find all of these differences and take a look at a graph. Okay, so I already entered this in some of my lists. Oh, here we are. List 4, I have those differences. So I'm going to graph that. And I like to do 2 different graphs. So I'm going to graph a normal probability plot, and I'm also going to graph a modified box plot looking for outliers, right? So let's do that. Got them both on the same viewing window, and you can see this is a very strong right skew, right? A quarter of the data are all the same. And that's why you can see on your normal probability plot this huge tail down here on the left. So it's pretty non-normal because of that skew. So that's a bit of an issue here. We can treat this as an SRS, right? It either says SRS or it doesn't really matter. If you're randomly selecting bags from a shipment, we can treat that as an SRS. And the population size for vitamin C is huge, so I don't have to worry about that. What is our sample size here, by the way? Let's take a look. Okay, so our sample size is 27, and we do have quite a bit of a strong right skew. So that's going to cause me to be a little bit concerned here. So I'm going to write that in my checks. But there are no outliers. So I'll say do to the strong right skew and a sample size of 27. I will proceed with caution while performing a t-test. T-test. Okay. The data should be unbiased and the population of product should be over 270, allowing the use of the standard deviation formula. Okay, so something that I want to talk about here is the whole proceed with caution thing. I mean, really, there aren't any outliers. In a sample size of 27, we're starting to get close to that kind of magical 40 number. So central limit theorem is kind of kicking in here, and no outliers. So we probably are fine to go. But I wanted to put this out there because this is what you do when you fail something or you might fail something. You just say, hey, this could be a problem. I'll proceed with caution. That's all you're doing. You're just alerting the person reading your work to look a little bit deeper at this if this is really important to them, right? Okay, so let's actually get the results. Okay. So we need to calculate our test statistic. Okay. So our test statistic, in this case it's a T, is going to equal, let's find the mean of list 4. Okay. That mean, negative 5.3 repeating. Okay, minus my null hypothesis, which was 0. Okay, over the standard deviation. Notice they didn't give me a standard deviation. Hey, that's why we're in chapter 11. So we're going to calculate right there sample standard deviation, and that's why it's a T. So 5.59. Okay. So let's work this out. I get a T of negative 4.96. Okay, again, that's if you don't round, right? Keep all the decimals in there. Oh, and again, just to show you where you find that, go to variables, go to statistics, and then when I click on, say, X bar, right, there it is. So you just enter that. Okay. All right, our degree of freedom was 26. So let's get a p-value. If I use my table, you can see I'm clear off the side. And yeah, I have to double it, but that means my p-value is less than 0.001, right? Doubling it. So we have very strong evidence that there is a loss in vitamin C. Okay. Oh, was it two-sided? I'm sorry, it was one-sided. My bad, don't double it. It's less than 0.0005. Okay, now here's how you can get the accurate result. We do, of course, have a test feature. This is a t-test. And we do have the data. Our null hypothesis was 0. This was in my list 4. And I was doing a left tail test. So there's my t, right? And you can check, yeah, that's the X bar I found. That's the sample standard deviation I found. That was my sample size. There's my p-value. And again, don't write 1.87. It's 1.87 times 10 to the negative fifth, right? It's a very small p-value. Remember, p-values are always between 0 and 1. They can't be over 1. So when you see a number here greater than 1, read to the end and get your scientific notation result. Okay. All right. So conclusion, we have very strong evidence. Hello.
I'm just custodian.
Okay, no problem. I'm just recording here. So we have very strong evidence to reject the null hypothesis. So we conclude that the average amount of vitamin C has gone down. Okay. So the mean vitamin C content has decreased. And there you go. T-test, matched pairs, T-test. All right, question B. Estimate the loss in vitamin C content over the 5-month period. Use a 95% confidence interval. Okay, so this is, in other words, do a confidence interval. Right? Notice it didn't say do a confidence interval. That they're not going to necessarily say that. They're going to say estimate. And you know, back in chapter 1, you would have said, oh, well, here's X bar. Well, now we know more. We can do a confidence interval. Okay. So we're doing a 95% confidence level. We need to take our X bar plus or minus our critical value, and we get that from our table. Now, please, 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 in chapter 10, we use the infinity row, so we're accustomed to that. A ton of students will jump right there and use that again. No, please understand, we're no longer using the infinity row because we're dealing with a t, not a z. So we gotta go up to the appropriate row. 26 degrees of freedom because our sample size was 27. So 2.056. Okay, multiplied by our standard deviation. I forgot what that was. There we are. 5.59 over square root of 27. Okay, so there would be our confidence interval. Again, you can now calculate that. Go to stat, go to test, and if you scroll down, you'll find a t-interval. And there we go. Calculating. There's our interval. Okay. All right, write our complete sentence. We are 95% confident the true mean loss C was between 7.544 and 3.123. I don't know what this was. Milligrams per 1,000 grams. No, 100. Okay. Notice once I said the word loss, then I didn't put the negatives, right? The word loss replaces the negative sign. Okay, letter C. Do these data provide evidence that the mean vitamin C content differs? Oh, this is a different question. Differs from a target of 40. So their goal is to have 40 as the average. I guess this is before being shipped. So let's do that real quick. So mu is 40, and this one just says differs, so not equal to 40. Okay. Now we're gonna have a little bit different test because we need to look at, let's see what list I have this in. List 2. Oops. Okay. So if you notice, this is much more normal, right? So this data set, this is the, factory vitamin C level, is awfully symmetrical, no outliers, nice, fairly linear, normal probability plot. So this is good. No issues with that data. So I would state the data are symmetrical, and the normal probability plot is fairly linear. So it is safe to assume normality. Okay. Other two checks remain the same, right? So we're taking forever here, so I'll skip those, just say same as before. All right, let's get our T test statistic with 26 degrees of freedom. So we need to find the mean of list 2, I think that was. And there we are, 42.85. Notice we have also a different standard deviation, 4.79. Okay, work that out. That's huge. I'm getting a T of 46.45. Is that right? No, something went wrong there. Sorry about that. Hit a wrong key. Again, anytime you get something that's really insane, go back and double check. I hit a wrong key, so it was 3.09. That's a much more reasonable number. So when I redid it, I got it right. I think I accidentally missed a decimal place up there. Okay. Now, that p-value, we can find that, again, using our table, 26 degree of freedom, 3.09 gives me a p-value between 0.001 and 0.0025. If we want a more accurate result, we can do a t-test. Okay. Oh, and double it, right? I forgot our alternative was two-sided. So if we use our table, we have to double those. But there's the accurate one, 0.0047. Okay, and conclusion. We have strong evidence very strong evidence that the vitamin C content at the factory does not have a mean of 40. Okay, and if you wanted to, you could now, check when it arrives in Haiti. What's run a test on that and see what it does compared to 40. But you get the point. Okay, moving on. 32. Give a 90% confidence interval for the mean time advantage of right hand over left hand threads. In that, do you think that the time save would be of practical importance? Okay. So I got to look back. Here's my data set. And I need to look at, again, matched pairs data, because this person did it with the right thread, this person did it with the left thread. Compare those two. Okay. So enter the data in the calculator, which I did right here. And again, subtract the two readings. Okay, which is list 3. All right, we want a 90% confidence interval. So I need to find the mean of my list 3. .32. Okay, critical value. My sample size is 25, so I go to a degree of freedom of 24. Okay, and I'm doing a 90%, so that's this row right here. Read up. 1.711. Okay. And multiply that by the standard deviation, which I have right there, 22.94 over the square root of 25. Okay. And then if you just want the calculator to do the whole thing, remember you do need to show that work though. Just go over to tests, choose a t interval, data, and there we go, 5.47 to 21.17. Okay, so we are 90% confident. The true mean time savings is between 21.47 and 21.47 seconds. Okay. Notice I skipped the checks. I'll just say the checks, right? Check for normality. So do a quick graph. Yeah, I think I might have it going there. Perfect. Nope. Just do the normal probability plot. I think it was 3, right? Okay. And normal probability plot looks pretty linear, so I'm going to say we're good on normality. We should have an infinite number, not an infinite, but close to an infinite number of subjects who could test threads, on these things. So standard deviation formula should be safe. And it should be good on biased data because we are doing a matched pairs format here, so we should be controlling for a lot of lurking variables. So there we go. All right, now, there is a follow-up here. Do you think that the time saved would be of practical importance if the tasks were performed many times, for example, by an assembly line worker, right? So if you do this once in your life, saving between 5 and 21 seconds, not a big deal. But if this is an assembly line worker that does this day in and day out, saving that much time on every single item, that can add up, right? So to help answer this question, find the mean time for right-hand threads as a % of mean time for the left hand. So find the mean of the two lists and divide. Okay, so I've got list 1 and list 2. I'm interested in those two. So this is a great time. I could just do 2 variable stats, huh? So I've got a mean of 104.12. Scrolling down, Y bar is 117.44. So divide those. And you can see about 88.7%. Which again, if you're doing this all day, day after day after day, you're saving over 10%, which is a pretty big savings in time. And of course, that means salary and, more, it increases your production and productivity, et cetera, and so forth. All right. Next question. Radon detectors. Many homeowners buy detectors to detect radon, which can kill you, by the way. It's not such a big problem out here in Southern California, but in other parts of the country, that's something that they actually have in their homes, radon detectors. Okay, how accurate are these detectors? To answer this question, university researchers placed 12 radon detectors in chamber, exposed them to 105 picocuries per liter of radon. There's the results. All right, letter A, make a stem plot of that data. Okay, so I have that in this calculator. Let's see, I put those into list 5. So first thing I'm going to do is put them in order. Now when I go to make a stem plot, right, I can see, now that I put them in order, it's going to be a little easier to make my stem plot. All right. So remember, when you make a stem plot or a histogram, you need to have at least 5 stems with some information in them. Okay, so I'm going to round these numbers off to the nearest whole number. So the 91.9 will round off to 92. Let's see, 95 would go into the next, I'm doing a split stem, right? The tens, I'm gonna have 0, 2, 4, 5, 5, 1, a 9, and the largest. There we go. So don't forget a key. Okay, so there's my stem plot. The distribution is somewhat skewed to the right. Yeah, okay. But not strongly enough to forbid use of T procedures. Again, I would prefer a normal probability plot if I had to pick one single graph. So I'll do that just to. Oh, turn off this other plot. And there you go. Normal probability plot looks pretty linear. So yeah, the data is not perfectly normal, but it's pretty close. So we should be fine. Should be safe. Okay, letter B. Is there convincing evidence that the mean readings differs from the true value of 105? Okay. So null hypothesis is 105. Alternative differs, so that means two-tailed. Not 105. Okay, we just checked for normality. Looks good. The number of readings possible here, lots and lots and lots, right? So we don't have any issue with using the standard deviation formula. Population is very large. And it should be unbiased data. We're just simply testing radon detectors. So I'm assuming they were not purchased with any bias method. Okay, so let's calculate our T. So we got to get a mean here. That was list 5. There we are, 104.13333. And our standard deviation, 9.4. And sample size was 12. So, working this out. Get a T of negative 0.32. There's nothing there, right? That's not even going to register on my chart. Less than, not even a half of the standard deviation away. Okay. So if you want to get a p-value, you're going to have to use, well, you could say it's more than 50%, right? Because two-tailed doubling that. Or you can use your calculator doing that and get a p-value of over 75%. So complete lack of evidence. So I guess I should give the p-value. And then conclusion there is a complete lack of evidence. To reject the null hypothesis. In other words, we cannot conclude any difference from 105. Okay. All right. Moving on. see, U.S. presidents when they took office. It does not make sense to use T procedures on this question or any inference. And here's the reason. This is not a sample, right? This is a parameter. So there is no need for a confidence interval when you have the entire population's data. Right? Pretty easy question. When we have the population data, we can simply calculate the parameter. Okay, there is no confidence interval when you have the parameter. It is what it is. That's the end of it. All right. 35, the power. Oh, fun, power of a t-test. Okay, so they're gonna walk us through this. Here's our null two-tailed alternative. Table C, what's the critical value for a 5% alpha? What was our sample size? 22. Okay, so we're gonna go to 21 for our degree of freedom. And our alpha was 0.05. Okay, and we are two-tailed. Okay. So that gives me right there. Oh no, I'm sorry, that is a one-tailed. We have a two-tailed. So we're right over there. 2.080. Okay. All right. Write the rule for rejecting H naught. Take S to be 0.3. Okay, so we have, I like to break this up into two pieces. I know the book just kind of leaves it as a compound inequality, but I break it up into two usually. So X bar minus 0 divided by, was it 0.3? 0.3. Over the square root of 22, not 21, not the degree of freedom, but n. Okay, and then we have positive. Okay, working those out. I'm getting positive or negative 0.133. Okay. So those are our cutoffs for rejection, and we will be rejecting whenever we're more than 0.133 away, right? So when X bar is greater than, the absolute value is greater than that, that's when we would be rejecting. Okay. Letter C, find the probability of this event when the true mean is 2. Okay. So here we go. Negative 0.133 minus 2. This is our t. And our other t is the one that's going to be closer and actually have some area. Okay, working those out. I am getting a z of negative 1.047. Double check that. Why did I write 2? 0.2. Yeah. I was looking at 2 and I'm like, wait a minute, that doesn't seem right. But yeah, it was 0.2. That's what I... Yeah. Okay, and then this side is the one that's going to be really large, large absolute value. So working that one out, it probably won't have an impact on our test. No, I'm getting negative 5.207. Oh, I'm sorry. And of course, they told us to make this a z because they gave me a sigma. So this is now a z. All right. So working this out, the probability that z exceeds negative 1.048 is approximately 0.85. So there we go. There is our power. All right, one more question. Yay. About 42,000 high school students took the AP statistics exam. For response, 5 open-ended problems and an investigative test. Just like that, still as of at least last year. Each free response question is scored a scale of 0 to 4. 4 being best, 0 being not so good. So here's a random sample of 25 scores. Is a sample of 25 papers large enough to provide good estimate of the mean score? Yeah, a sample of 25 is good enough. Yes. Assuming an unbiased selection method, which they said random, so it should be good. All right, letter B. Do you think the population of scores on this question is normally distributed? Why or why not? Okay, so here's where we got to graph, yay. So I have this data in list 6, and that means I'm gonna do normal probability plot of list 6, and we may as well throw in the old box and whisker as well. So there's our plot. I think I might have accidentally done this on the earlier problem. Whoops. I think I graphed the wrong list earlier. Sorry, go back, regraph. But yeah, this is very heavily right skewed, and you could see big tail there on the left on the normal probability plot. So sorry about that, guys. This was the wrong list because that graph looks identical to the one I did on our first graphing problem. I hit the wrong list when I graphed. Sorry. So B, no, this is not normal. Okay. Okay, letter C, construct a 95% confidence interval for the mean score. Okay. Again, our checks, looks like we're proceeding with caution on the normality. There's more than 250 scores, right? Because 42,000 people took the test. So standard deviation formula is safe. And lastly, the data should be unbiased because the papers were randomly selected. So proceed with caution on the normality front. Again, I'm not writing it out because this is taking forever as it is. Okay, so we're going to do our mean of the 6. Wow, pretty terrible mean, 1.04. Okay, on our critical value for a 95% with 24 degrees of freedom, right here, 2.064 multiplied by sample standard deviation of 1.136. Square root of 25. So there's the work. To get an accurate result, go to test, choose a t interval. Data is in list 6, and we were doing 95%. And there's our interval. And again, I like to always check, make sure that I get the same X bar and S that I wrote down. So that means I got the right list, which I messed up earlier, sorry. So, all right, we are 95% confident. Be true. Mean score is between 0.57 and 1.51. Okay, there we go. That was great fun. Thanks for watching, and come to office hours if you have questions.